Hello everyone. In this relatively short video, I want to talk about the difference between sample variance and population variance. I don't know if you noticed or not, but when you look at the variance of a population, which means basically a lot of data, you see that the way they calculate the variance, they subtract each data from their average, sum the square of these terms up, and divide it by the number of data points. But if just it's a sample, which means a lot less data than the population, they do the same thing. They sum the square of these deviations, where x bar here is the average of the sample instead of mu, but instead of dividing it by n, they divide it by n minus 1. So n is the sample size. They have this extra 1 here that they don't have in the sigma. So if sigma squared is variance of population and s squared is variance of the sample, the question is, where does this 1 come from? Why are they not using the same formula? I remember I asked this question when I was in grad school passing a statistics course, and when I asked, the professor said this is because they want to remove bias. And when I said, what is bias? Because I have never heard of it before that, and said, what is that and how does it remove bias? And she could not answer me. She said, it's bias. It's just they wanted to remove bias. And well, the answer was she didn't know. So here I want to show you basically why this 1 is there. It's not just as simple as you think, hey, we just added a 1. Because you might ask, why don't you subtract the 2 or 3 or add a 1 or 2, huh? So this extra 1 that we subtract here is called the Bessel correction. And I'll tell you what the bias is. So it removes the bias of sample variance. What does that mean? Well, I can show you that if I don't remove that n minus 1 and just go with n, when I increase the number of data in the sample and make it closer to the population, I can show you that this s squared is not going to exactly estimate sigma squared, right? So when you make this number of data in sample bigger and bigger, ideally your x bar should converge to mu and your s squared should converge to sigma squared, right? But it doesn't. X bar does converge to mu, but s bar does not converge to sigma squared. Actually, it does converge to n minus 1 over n times sigma squared. So you see, it does not exactly converges to sigma. It converges to something a little bit smaller. This number is less than 1, right? So if n is like, I don't know, 100, this is going to be like 99 over 100 times sigma squared. And this difference goes away only when n is infinity. And in reality, we never have any population with infinite members. Okay, this n, the population number, is always a finite number. So you see that there is a difference between actual sigma squared and this s or sn squared. There is this difference between them, which is equal to 1 over n times sigma squared. And this difference here is called the bias. Okay, so the goal is we introduce that negative 1. If we do that, it should take care of that bias and remove it. Really, yes. So let's show the proof of that. So the first thing I do is the correct sample variance that has that n minus 1 in it, I'm going to call it s squared. But the version that does not have that minus 1, it only has n in it, I call it the biased sample variance, and I show it by Sn squared. Okay, so Sn squared is the one that is wrong, is the one that has this n instead of n minus 1. So I call it biased sample variance. And the one that we always use in statistics, the one that has n minus 1, I call it unbiased sample variance. Okay, so s versus s squared versus Sn squared. Right? So now, to show this important thing, this is what I need to prove. To show this, first I start by claiming that, well, the sum of the xi minus x bar squared for the sample I goes from 1 to n, sum of the square deviations, is equal to sum I goes from 1 to n of xi minus the population average squared minus n times the difference between the sample average and the population average, the whole thing squared. So the first thing I claim is that these two left-hand side and right-hand side are equal. And you might say, well, where do you get that one? So first I need to show you this. So let's go ahead and do that. For that, I'm gonna start with this right-hand side and I'm gonna expand it. So I'm gonna square this. This is gonna go summation I goes from 1 to n of what? It's gonna be xi squared plus mu squared minus 2 mu times xi. The second term in it is not inside the summation, so it's just going to be negative n times x bar squared. Negative, sorry, it's just squared. Negative n times mu squared, and then positive 2n mu x bar. Okay, so this is what you have if you expand it. This is the second term, this is the first term. Now what? Now this mu squared is a constant. I can just take it out of the summation. So it's going to be summation of I goes from 1 to n of xi squared. And then plus mu squared times summation of I goes from 1 to n of 1. And then for this third term also, the negative 2 times mu is constant, so I can bring that one also out. So it is going to be this. And then the rest of it. Okay? Now what? Now, summation I goes from 1 to n of 1. This is going to be n, and summation of all of the numbers go from 1 to n. This is going to be n times x bar. That's the definition of x bar. X bar is summation of these numbers divided by n. So if I cross multiply, that's n times x bar. So if I simplify, what would I get? Here is going to be summation of xi squared. And then this one is going to be plus n times mu squared. That is going to be negative 2n mu x bar. And then minus n times x bar squared. And then minus n times mu squared. And then plus 2n mu x bar. And now if you see, some terms would cancel out. These two terms would cancel out. And then these two terms would cancel out. So it's just going to be summation of xi squared minus nx bar squared. So this is your right-hand side, okay? Now what about the left-hand side? What happens to the left-hand side? So here, we're going to grab the left-hand side and we're going to expand the left-hand side. If we do that, this is going to be summation of xi squared plus summation of x bar squared minus 2 times summation of xi x bar. Okay, now what? Now x bar has nothing to do with the summation. It's a constant. You can bring it out. So this one is going to be x bar squared comes out. It's going to be summation of 1, which is n. So this one is going to be n x bar squared. Here x bar can come out. It's going to be summation of xi, which was n x bar, if you remember. So this whole thing will be 2n x bar squared. And then plus summation of xi squared. And now nx bar squared and negative 2nx bar squared, if you simplify, that is going to be negative nx bar squared. Okay, so this is the left hand side, And here, this is the right-hand side. And you can see they're exactly the same thing. By the way, this is a squared, of course, sigma xi squared. You see that the left-hand side and the right-hand side are the same thing, okay? So when I claim that these two are the same thing, clearly you can see the proof of that. Good. Now that the left-hand side and the right-hand side are equal, I'm going to apply the expectation function on both of them. And you know expectation is a linear operation, so here on the right-hand side, it is going to go like this. Yeah? And you're going to get this one. Good. Now, here we assume that all of the data that you have in your population and as well in your sample, they are IID. And you might say, what is IID? IID means independent, and also what? They are identically distributed. So they all come from the same distribution, and they are what? They are all independent from each other. So the probability of picking one and another one have no independence, right? Okay, and if you want to know more about independence, I have a video. I talked about basic terms of probabilities, and you can see the definition of independence. So basically, it's like P of xi and times P of xj. This is the same as the joint probability. Or that is the independence, right? So or another way they can write it is to say that P of xi given xj, conditional probability, is the same as P of xi. In other words, whether xj happens or not, it has nothing to do with xi. Okay, so this is the definition of independence of two samples. And identically distributed, of course, means they have the same distribution, so they have the same average, they have the same variance, they come from the same distribution. Now, because these data are IID, or independent and identically distributed, and they are coming from a population with variance of sigma squared, then the first term on the right-hand side, which is this guy here, it becomes equal to what? If you look at this, this is the expectation of each one of these data points minus their average of the population squared, right? That is exactly going to be n sigma squared, because if you look at the definition of sigma, you see, we are looking at this term. And so if I cross multiply both sides by n, you see that is exactly n times sigma squared in terms of expected value. So this term here, the first term on the right-hand side, is going to be n sigma squared. The question is, what is the second term? What about this one? Now, for the second one, I need to first show you something, and then I can show you that the second term, which is expectation of n times x power minus mu squared, that guy is actually just going to be sigma squared. Okay, so let me first show you where that one comes from, and then it's over. So here, this is my claim. I say that if I look at the averages of the samples that I take, so if the average of each one of these samples is shown by x bar, right, in general a variable x bar, I can show that if this x bar is defined as a variable itself, right, so you take one sample, you take the average of it. You take another sample, you take the average. Another sample, the average. So if you look at all of these averages of these different samples with different sizes, you can basically say this is its own random variable, where you can show the average of them is mu, average of all of these x bars are mu, but the variance of them is equal to sigma squared, but divided by n. Okay, so the average of the variance of the samples is not sigma squared, it's sigma squared over n. The variance of the data, original data, is sigma squared, but the averages of the samples, their variance is smaller, is sigma squared over n. So where does this come from? Let's take a look. So I say, what is the definition of variance of X bar? Means the variance of, based on the definition of X bar, sum of the data in the sample divided by the number of data in the sample. Good. Now we know from the probabilities that the variance of a times y, where y is a variable and a is a scalar, is a squared times variance of y. Okay, this is not really hard to show. This is basically a very primary or basic term in definition of variance. Okay, yeah. So if you have a times y, the variance of a times y is going to be basically 1 over n of summation of a times y minus the average of a times y, which is a y bar, and then this whole thing squared, and you can factor out a and bring it out. So it is going to be a squared summation of y minus y bar squared. And if you bring this a squared out, this summation over n, that is sigma squared, so it's going to be sigma squared over n. Okay, and sorry, sigma squared times a squared. I'm sorry, sigma squared times a squared. So that summation over n is sigma squared, and then of course multiplied by a squared. So you see, when I multiply a variable by a, the average multiplied by a, but the variance is multiplied by a squared. Okay, so that's not really a big deal to show. Fine. So here I can say this summation is my y, and a is that coefficient 1 over a, 1 over n. So if that's the case, I can bring this 1 over n out and square it. So it's going to be 1 over n squared, and then variance of these summations, right? Now the question is, what is the variance of some of these numbers? So here I can swap the summation and the variance operation. So it's going to be summation of variance of xi. And this guy, the definition of it is sigma squared. So it's going to be summation of I from 1 to n of sigma squared, which is going to be n sigma squared, because sigma squared is a constant. So it's going to be n of them. So now this n sigma squared is going to sit here, and 1n with 1 is n squared. This simplifies, and guess what? You can show that the variance of x bar is actually sigma squared over n. Okay, so this thing that I claimed here, this is exactly the proof of it, can be seen in the green box. Fine. Okay, now if that's the case, now let's go back and look at the second term of the right-hand side of that equation here. So the left-hand side, I showed that the left-hand side is equal to n sigma squared. That's called equation 1. Now for the right-hand side of it, let me show you what the right-hand side becomes. So look at the right-hand side. The right-hand side is expectation of n x bar minus mu squared, right? Okay, so what is that one going to be? So this n is a constant. I can bring it out of the expectation. So it's going to be expectation of x bar minus mu squared. Exactly the definition of variance of x bar, right? Because I'm subtracting x bar from the average of all the x bars and square them. Expectation of that is variance of x bar. That's the definition of variance of x bar times n. And I just found that variance of x bar is sigma squared over n multiplied by another n. They would cancel, so I just get sigma squared. There we go. So I found that the right-hand side term is sigma squared. The left-hand side term is n sigma squared. So if I subtract, the left-hand side is going to be n minus 1 times sigma squared. And that is exactly what you can see here. So the left-hand side is n minus 1 times sigma squared. Now, what was that biased sample variance, Sn? Look at this. This was what we wanted to focus on and take the limit of it. So that was the definition of, look at it, that's the definition of sample variance. Each data is subtracted from the average of the sample, squared, summed together over 1 over n. And if you look at here, look at this guy, the left-hand side here, which we just calculated, that's basically this one, except for that 1 over n. Everything else is the same. So I can say that this guy here, this left-hand side, this is that Sn squared. The expected value of this Sn squared is equal to 1 over n times this guy, which is n minus 1 over sigma squared. There we go. So it's this. So this is the final result. So look, what would be the expected value of the biased sample variance? Is n minus 1 over n times sigma squared. It's not going to be sigma squared. It's this underestimated version of it, which is n minus 1 over n. Okay, and here I need to clean this up. It's n minus 1 over n, really, not n over n minus 1. So clearly it is underestimating it. There is some bias. Yeah? But if instead of this definition, I had here some n minus 1, then when I calculated this one here, this guy would have been n minus 1. This guy would have been n minus 1, and then this n minus 1, this n minus 1 would cancel, and guess what? You see that the expected value of the one that has no bias is exactly sigma squared, which is what it should be if you don't want bias. So now you see that why, after all of these proofs and everything, why is it that when we take a sample, we always subtract a 1 in the variance and we just don't leave it with n as we do with a large number of data points? Good. So finally, now we can understand what we call this Bessel correction, this extra 1 here. That you see there is a lot of proof behind it. Now, two things. One is that a biased version of variance, that guy has a name. So the one that has n in it instead of n minus 1, this one, the one that has n in it, although we don't use it in statistics, but it has a name and it has applications. So although we don't use this guy, but it has an application and name. We'll talk about it later, but if you want the name of it or the use of it, it's called the maximum likelihood estimate of the population variance. So that one is the maximum likelihood. So if you use maximum likelihood and try to estimate sigma squared, the thing that you will find is Sn squared, okay? And it's always biased. So although it's the maximum likelihood, it doesn't mean it's without any bias. Now, you might say, well, you showed me all of that with a lot of proof and everything. Is there any way that I can understand why you use this extra 1 kind of intuitively and without a ton of mathematics? And you might say, yes, kind of. So here, the intuition is like this. When you calculate the deviations of your data from the sample mean, so you calculate the sample variance, some of these deviations should be equal to 0, right? You see that sum of the xi minus x bar, if you sum it up over all data, this should be equal to 0. Then pay attention, there is no power 2 here, okay? This is just power 1. And this is obvious, correct? Right? Because here, this is going to be summation of xi minus summation of x bar. And this is going to be nx bar, and this is going to be nx bar. So, of course, it is going to be 0. So, sum of all deviations, not deviation squared, sum of all deviations from the average is 0. Okay? If that's the case, that means from all of the n data points that you have, if you fix the sample, not all of them are going to be free. Well, what does that mean? Means, for instance, if I say, hey, give me 5 numbers, the average of which is 6. Okay, so give me 5 numbers, x1, x2, x3, x4, x5, such that their average is equal to 6. How many of these x's can you freely determine? The answer is only 4 of them, because the fifth one should be such that their average is 6. Okay, so only I really have, out of n numbers, I have n minus 1, in this case 4, of the numbers are free to be selected. So my degrees of freedom is actually n minus 1 or 4. Therefore, when I calculate my variance, instead of using n as the degrees of freedom, I use n minus 1. Okay? Yeah? So that is kind of an intuitive way to look at it, but I, in this case, prefer the rigorous math and the proof of that. So if somebody says, what is Bessel correction? Why is the standard deviation, why is the variance of a sample formula is different than the population? Why one has n1, n minus 1? You have the answer to it. Hopefully this video was useful to you. It went a little bit longer than expected, but it needed rigorous math proof. Thank you so much. I'll see you in the next video.